Okay, hello everyone. Welcome to this session. Okay, so I'll share my screen and we'll start. Can somebody please confirm whether I'm audible and my screen is visible or not?
Yes, ma'am.
Yes,
you
ma'am.
are
Okay.
audible.
Okay, thanks. All right. So let's get started.
Ma'am, before that, actually, I need to ask you something.
Go on.
Actually, yesterday, I was having some internet issues, so I was not able to attend my workshop. But I watched it on YouTube.
Okay.
So, will that affect my certification eligibility to for certification?
Okay, so you will be expected to submit some assignments.
Yeah.
Uh,
I mean, yesterday I was not able to attend, so
yeah, got
attendance.
that. Yeah. So we will see that, no problem, don't worry. So one of the important criterias for OPP eligibility will be you people submitting the assignments, which we'll be sharing with you. We haven't shared with you yet, right? The details of the workshop course, or have they been shared?
No, ma'am.
They're yet to be shared, right? So you'll get the details and you will have to submit the assignments there. So based on that, we'll decide the eligibility for OPP. So don't worry about that, okay? Although we'll be checking the attendance as well. You have to have good attendance. But if there was some issue, that will be taken care of, okay? Is that
Thanks a
okay?
lot, ma'am. Thanks a
Okay,
lot.
no problem. Okay, so let's get started. So this is how we'll proceed. In this session, we are going to cover K-means and Perceptron. So first half will be on K-means, second half on Perceptron. So what we will first do is we'll understand the very basic details of K-means that are necessary to be able to implement this technique. Okay, so we will briefly cover this for a few minutes and then we'll move on to code. All right, so I hope, so given that the prerequisite was that you should have done MLT, so I hope you all are aware of K-means. We know that all ML techniques can be divided into supervised and unsupervised ML. K-means is a type of which technique? Unsupervised ML technique, where we don't have labels. We have the feature matrix, capital X. Okay, we have the feature matrix, and in unsupervised ML, we have to look for the patterns, different kinds of patterns which are present in the data. And one of the important patterns that we are interested in is finding whether there is a good clustering that is present in the data or not, which means whether the data points are kind of clustered together or not. Okay, so that's what K-means does. So this is the kind of data that is given to us. We have the data points, no labels, x1 up to xn. Each data point is in d dimension, assuming that the number of features is d. The objective is to partition these data points across clusters. For example, let's say this is a kind of data, right? This data visibly, we see, you can see this is because this is in 2D, we can see through the plot that there are clusters, 3 clusters present in the data. The objective here is to partition these data points in different clusters. In this case, 3 clusters, so K is going to be 3. Here, the data is in 2D. This is your feature 1, this is your feature 2. So we can see that. But in case of several features, obviously we'll not be able to plot like this. So we'll not be able to see whether a good clustering is present or not. So we need some systematic way to check whether there are clusters present in the data or not, and if there are, how good or bad they are. So that's what we do in K-means. Now, this is actually an NP-hard problem because partitioning the data, let's say there are n data points, and we have to, partition them across K clusters. Can somebody tell me what is the maximum number of possibilities that can be there if you have to partition n data points across K clusters?
K power n.
K power n.
Correct.
K
So
power
12.
n.
Correct. K to the n. So for the first data point, it can go in any one of the K clusters. For the next data point, it can go to any one of the K clusters and so on. So that gives you K to the n. This is a huge number, right? So there are several possibilities and we cannot try out all of them. That's what makes this problem an NP hard problem. But there are some heuristic approaches that we can use, and that is what is given to us by k-means. Okay, so we'll see what is the approach that k-means or Lloyd's algorithm gives us. And then we'll move on to code. Okay, so there's one thing that we'll be using in code as well. So let me introduce that terminology to you. Let's say there are 4 data points. We will keep a record of which cluster they are assigned to. Let's say k is equal to 3, which means three clusters they can be part of. So we will keep a record of which cluster each data point is assigned to. So let's say I assign them like this. So this shows that x1 and x2 are part of first cluster, x3, x4 are part of second cluster, x5 is part of third cluster. So this kind of record we are going to keep in Z. So this is your Z1, this is Z2, and so on. So this is what Zs are going to contain, which we will be calling cluster indicators. We are going to use this in code as well, so it's good to be aware of them. So the possible values that Z can contain are one of the cluster numbers. If there are 3 clusters, there will be 1, 2, 3. Okay. Now let's talk about what is the k-means algorithm or Lloyd's algorithm, which we are going to code. It's a simple algorithm. Some 3 steps are there. First step. So we will initialize the cluster centers, and this is randomly done. Okay. So let's say these are the data points. Okay. These are the data points. We will randomly choose. So we will initially decide some k value. Please note, in k-means, k is a hyperparameter, which means this is something that the data scientist has to provide. So in the beginning, we will fix it on some value. Okay, let's say k is equal to 3 in this case. We can talk about later on whether, how to find this value of k. That's another point that you should be aware of. Anyway, so let's say we fix on k is equal to 3. So we will randomly choose 3 data points. These data points could be anywhere because we are choosing randomly. Let's say these 3. Okay. This is first step, initialization of cluster centers. Okay. And also this will also include initial assignment of data points to clusters. Now, what do we mean by this? For each data point, we will check which of these 3 is closer. Okay. And for that, we'll use Euclidean distance. For example, for this data point, we will check the distance from this cluster center. We can call it C1, C2, C3 or whatever. So for each data point, we are going to check the distance from each cluster center. Whichever cluster center is closer, like you see here, C1, C2, C3, C1 is closer to this data point. So we'll assign this data point to C1. We can say that this data point is assigned to C1. Okay. We will do this for each data point. Okay. For this data point, let's take one more example. We'll check the distance from each of these 3 cluster centers. Let's say this is closer. So we'll assign this cluster center C3 to this data point. Okay. This is called initial assignment of data points to clusters. Now every data point has been given some cluster. Now comes the iterations. So k-means is an iterative algorithm. This is initialization, which is performed only once. Okay. After this, the second step, we keep on repeating certain steps. And those steps are these. Let's call them 2.1 and 2.2. And this goes on until convergence. We'll get back to this later. What do we do in each iteration? Every data point has been assigned some cluster. Okay. Based on that, we'll find new cluster centers. we'll compute new cluster centers. Okay, so let's get back to x1, x2, x3, x4, x5. Let's say x1 has been assigned to cluster center 2, x2 has been assigned to cluster center 1, x3 has been assigned to 1, x4 to 2, x5 to 3, let's say. We'll compute new cluster centers. How do we do that? So cluster center 2, x1 has been assigned and x4 has been assigned.
Average.
We'll take the average. So x1 plus x4, in this case, there are only 2 data points. So this is going to be divided by 2. This is the cluster center for the second cluster. Okay, this is the new cluster center. Same ways, we will be computing C1 and C3 as well. These are new cluster centers. So this is this step, compute means of all clusters. Cluster centers or means, one and same thing. Okay, people use these two terms interchangeably. Now our
And we will
means
take
have been
average of x2 and x3 also.
correct. For C1, we will do x2 plus x3 divided by 2. For C3, there is only 1, so we won't take, right? So, but in general, there'll be more data points, so we'll take the average for all of them. Now, you see, after initially C1, C2, C3 were here, but now we have computed new C1, C2, C3, and obviously they will change their position. Let's say now they move, C1 is here, let's say C2 is here, let's say C3 is here. Now they change positions, right? So there is there are new cluster centers that we got. Now the next step is reassignment of data points to the clusters. We just now did some reassignment initially, which means for each data point, we checked which cluster center is closer. We are going to perform that step again. For example, for this data point, we will see which of the new cluster centers is closer to it. These green ones are the new cluster centers. So for each data point, we are going to check which cluster center is closer. This data point was already assigned to this one, and this is the closest to it. So this data point will not change cluster. Let's say there is some data point which finds a new cluster center which is closer than its already assigned cluster center. Then what we will do? We will do the reassignment, which means, let's say there's some data point xi, and it had been assigned to cluster center C1, but now again, since cluster centers have moved, let's say xi is closer to C2 now. So what we will do? We will do reassignment. Earlier xi was assigned to C1, but now xi will be assigned to C2. This is called reassignment. Okay. We do this for each data point. So which means if earlier this setup was like this, let's say now it becomes 2, 2, 1, 2, 3. So we can say that these data points were happy in their position. This data point was not happy because it found a cluster center which is closer than its already assigned cluster center. So it will move, which means it will be reassigned. Once they are reassigned, again, we will compute means. Obviously, the means will change because the data points have changed, right? Again, you see, the means will change now, right? This is something that keeps on repeated, that we keep repeating until convergence. Now, what is convergence here? When there are no more changes to cluster centers, okay, that is what indicates that k-means has converged. So there will come a point when there will not be any change in the cluster centers. They will remain wherever they are. They will not change position because every data point is happy in their own position. That is when we say that k-means has converged. So this is the simple algorithm of k-means, which is what we are going to code. Any doubts so far?
Ma'am, what if
Yes.
2 points are equal distance to 2 cluster points?
Yeah. So we need some way to break this tie, right? So in that case, we randomly assign one of them. So if you see sklearn, which has an implementation of k-means, right, which you'll do probably later on in MLP if you've not done. So that does it like this. If there is a tie, it randomly assigns, right? Something we have to do. Okay.
Will there
Now,
be a scenario, ma'am? Will there be a scenario in where the k-means don't converge?
k-means always converges. So there's an extensive proof behind that. So basically, I can give you a quick idea. After every reassignment, the distance of each data point from their center reduces. So this is a monotonically reducing thing. Okay. So that makes sure that it will never shuffle back to it will not go back and forth to the, let's say first it goes to a particular data point, goes to C1, then it goes to C2, then it comes back to C1. That can't happen because of this very fact that the distances are going to reduce only. Okay. So this is one of the important point in the proof of convergence. You can look at the convergence proof. So k-means always converges.
Okay.
Ma'am, I have a question not regarding this k-means. What is the goal of the system, ma'am? The k-means and what?
What is the goal of, sorry?
Goal of the system is k-means coding and what? Is there anything else in this going to happen in this?
So your voice is not
Perceptron.
clear.
K-means and perceptron.
K-means and perceptron.
You're asking what is it that we are going to cover today, is it?
Yeah.
Okay. Yeah, k-means and perceptron. Yeah.
So, ma'am, is it necessary that we should always take the mean to determine the center of the cluster?
That's how k-means works. That you can see that means is there in the title itself, but there is another reason why we take means, because if there are some data points that are given to us, the point that will be if you find the distance of each data point from a particular point, and you want that distance to be minimum, then that distance is going to be minimum from the mean only. Okay, again, there is a proof behind that, and that has been covered in the lectures if you have seen.
But what happens if the data is having outliers? Then the convergence will take long time.
See, if the data has outliers, then it depends what is the initialization that you do. Okay. So let's say when you initialize, so I said that we randomly initialize the data points. Let's say out of that random initialization, one of the initial cluster centers you take, which is an outlier. So that might affect the output of k-means, right? But again, it will always converge. That is for sure. But you can find different results from k-means. So in one run of k-means, you had different cluster centers, initial cluster centers. You will get one result. In another run of k-means, you had different initial cluster centers. You will get another result. That is possible. Okay, that is why in practice, what we do is we run this k-means some number of times, let's say 10 times. For example, in sklearn, by default, we run for 10 times, and whichever gives the least loss, we consider that configuration. Okay, so outliers effect can be managed in that case by having different initial cluster centers. Or what you can do is you can go for k-means plus for initializing the cluster centers. Okay.
But can I use median to determine my cluster center?
If you want to use median, you can try that out. So there's something like, I'm reminded of something, some technique which uses median, but I'll have to look that up exactly, how, what is the performance of that technique with respect to this k-means. We can check that out how the output will vary if you take the median. But I'm telling you the reason why we take mean is because mean is the point which is the closest to all the data points. If you sum up the distances from each data point, mean is the point that is the closest. Median may or may not be, right? So how that will affect the performance, that we might need to check.
Okay.
Okay, so let's get to the code. Yeah.
Ma'am, the collab notebook is not shared over the link over the phone.
Yes, ma'am. Please share the collab notebook on the day one folder.
Yes, ma'am.
No, day one and day two, did you get? Is it?
Yes. Day 3 is
this
not
one
there.
I'll share after the session. Is that okay?
Ma'am, we wish to code you
Ma'am,
actually with
no,
you.
we want to
We can
code
also
along with
code
you.
along with you.
Along with you, ma'am, we also code on our collab. So, ma'am,
Yeah.
please share if possible.
You want to code, is it? Okay, so give me a moment. I'll have to look for that folder and copy things there. Okay, you want to code along, is it?
Yes, ma'am.
We usually
Okay,
code
give me a
along.
moment. Give me a moment. Yeah. Do you have the link of that folder? Do you
Yes,
have the
ma'am.
link? Can
Yes,
you
ma'am. It is
put
just
chat?
tiny.cc.
Yeah, just share
Someone
it in the chat,
share,
please.
Yes.
someone share on chat.
Yeah. Okay. Okay.
Ma'am, I have a small question regarding the convergence of k-means.
Mm.
Uh, so in the lectures, an example was given where the data points were kind of arranged in a circular fashion, and it was said that since the k-means will fail to separate these data points into Voronoi regions, the k-means will fail here. So is that an exception case, or will it really converge in that case also?
It will converge, but the clusters will not be good.
Okay, so they will not be optimal, right?
They will be bad. So one circle inside another circle, right?
Yes,
So
yes.
you will get kind of half circles, right? Which is not what you are kind of looking at through k-means. But k-means, the way it runs, it will provide that kind of output. So you might want to look at some other clustering techniques if you want to well cluster such a data set. So some kinds of data sets, you cannot use k-means to cluster them well. Okay.
In that case, if you do the log of the data, then that circular can be converted.
Some such technique, kernel technique you would have to use, or there are other techniques like spectral clustering and all. So you might have to use such techniques. Either you transform your data and get back to k-means, like kernel k-means, or some other technique like density based HDB scan, like that. So they might be able to do better. Okay, can you people confirm whether you got this collab I pasted there?
Yes, ma'am.
Yes, ma'am. Yes, ma'am. We got. Thank you, ma'am.
So yeah, no problem. Okay, so let's get started. Okay. All right. So before we proceed to coding k-means, there are some functions that we are going to use. Probably some of them you might have done before. If you have done, this is going to be revision. If you have not done, this will be helpful for implementing k-means. So let's go over these functions. I am just importing Numpy. So several functions from Numpy we are going to use. For example, these initial cluster centers that we spoke about, randomly chosen. We'll randomly choose initial cluster center. So for that, we need some function to randomly choose. So let's go over a few functions from numpy.random. So numpy.random, we have numpy.random.choice. There's a function that we can use to random. So this has several variants. If you pass only one integer inside this, it will give you a random number between 0 and 10. Okay. Once again, you run this because this is random choice. So every time you run this, you're going to get a different random number, right? So this is one thing. If you want multiple elements, so by default, you get only one element. If you want multiple elements, then you can pass another parameter, numpy.random.choice, let's say 10, 2. This means that I want 2 random numbers from 0 to 10. I run it again. I get some other 2 random numbers and so on. There's yet another. No, this is a list. This is a list of 2 random numbers. This is basically an array. Yeah, this is exactly an array because you're using NumPy, right? So the output will be in a NumPy array itself, which contains 2 random numbers between 0 and 10. If you pass 3 here, you will get 3 random numbers. There's one more variant of numpy.random.
Is 10 inclusive?
This is inclusive. One moment. This is inclusive. Yeah, looks like this is inclusive. Let's check. Let's check more numbers. Doesn't look like it. We are not getting 10. So looks. Oh, we are starting from 0, right? We're starting from 0. It will go up to 10 minus 1, right? 0 to 9. Okay.
Okay.
Okay. One more variant, which is going to be more useful for us today in our code. You can pass a NumPy array itself. Let's say we have a NumPy array. Let me call it A1. So NumPy.array. I'll create an array and some values I'll pass there. Okay. Now this array I will pass here. This will give me one random number from this array. Every time I run this, I get a different random number from this array itself. Okay, this is something that might be useful. In case we are interested in multiple values from this array, we can pass that. For example, I'm interested in 3 random values from this. Okay. So this is your numpy.random.choice. Random. Yeah.
When I did this, I got 4,4. So repetition is possible.
Yes, this is with replacement. Okay, repetition is possible. This thing might be small, so you might be getting repetition very quickly. But if there are a huge number of data points, I mean, repetition you can get, but that will be not so often, right? But definitely it is with replacement, which means once you choose a data point, it is put back again to be chosen once again also. Okay, so that was numpy.random.choice. Then next is numpy.random.seed. So this seed is used to make things predictable. Now, what do I mean by that? So you saw this, right? numpy.random.choice. If I do this, I get some random number. I run it again. I get some other random number, and so on. Similarly, if you run this code, you will get some other random number. I'll get some other random number, right? If we want to make sure that across different executions of this code, I should get the same random number, or we want to make sure that you also get the same random number that I'm getting, then we can set some seed, because inherently it is not actually random number generation, it's pseudo random number generation, which means some kind of technique is followed internally, and that technique requires some seed. And if we can pass that seed from our side, that seed will be used. We can pass any number as a seed, no problem. So I got 5 now. Once again, I executed. I got 5. Every time I'm getting 5. So this is making things, so this is something that you can use for reproducibility. Okay, even if you use the same seed and same code, you will get the same random number. So this we can use.
They're getting 5 only.
Seed of 0, what is it telling? Is it index number?
No. So like I was telling, it's not purely random number generation. It is pseudo random number generation. Pseudo means it tries to give you a random number, but there is some kind of seed that it uses. Okay. And if we give the seed from our side, always that seed will be used. So you can imagine that there's some technique internally that is followed to generate this random number 5. And we are giving the initial, input to that, algorithm that is internally followed by Python to generate a random number.
You mean same number has to repeat in any time, any time you want to
Your
run.
voice is not clear. Sorry, can you repeat?
You are trying to get same number in multiple times.
Yes, multiple executions will give you the same number if you use a seed. Okay.
The seed number could be anything.
It could be anything. Yes.
Ma'am, can't we predict the number? Here it is 5. Suppose if I want 8, can't we predict
No.
it like...
No. If for that you need to understand what algorithm is used internally by the pseudo random number generator. Probably you can get to see that through the source code, but you need to be knowing that algorithm. You need to be able to implement that if you want to generate this number yourself. Okay.
Okay.
Ma'am, as you have chosen the number 0, I'm also doing by choosing 0, I'm also getting 5, the same number. So is it for 0, 5 is assigned already? Is it like that?
See, imagine something like this. Imagine something like
Adding
this.
some
Let's
line
say,
in the same thing, ma'am. Sorry to interrupt. While I am using seed 2 or seed 3, then 8 is coming.
yeah, you're using a different seed, right? So you will get a different number. What is the confusion there?
I was saying, ma'am, for you are running the code, I am running the same, and I also choose the seed 0, and for that I'm also getting 5. So is it, we can say that for a seed, if anyone choose the seed as 0, everyone will get the 5.
Yeah. So that I'm going to answer, but somebody else asked the question just now, so I was trying to understand that. Anyway.
Okay. Sorry, ma'am.
No, your point is clear, and that's what I'm going to talk about. So I'm just giving a small example. Let's say some input I expect, let me call it I, and then I have some method that I use to generate a random number. I'm just using a very small example. Let's say the random number that gets generated is equal to I plus 2 I square. Just a simple example. Now, if I is 2, right? Then what will be your R?
6. Sorry.
10, right? 10, right?
10, yes, ma'am.
Now, if I pass I to be 1, then what will be your R?
It's 3.
Correct? So it's similar to this. The random number generator, pseudo random number generator is not this simple. There are several things involved there. We can check that out in the source code. What exactly?
So it's similar to a hash function.
Not exactly hashing. So if hashing is being used here, then fine, it is similar to hash function. But I'm trying to show you the connection of the seed with the output. Why we are getting the same output when we are passing the same seed. Okay.
Ma'am, can we give 2 number inside the seed?
No, it wants only 1.
Like 11, 12.
No, it expects only 1 parameter. Seed wants
parameter is 1, like
actually asking
11
2-digit or more digit numbers.
Yeah, you can pass.
Can you give 0, 1 or something like that? 0, 9. 0, 9.
0, 9. No, 0, 9. What does that mean?
9 only.
Yeah.
So can we give that? You can take a 0, 1 only. Instead of 1 0, you can take. Can you take 0 1?
No, 0 1 is not an integer, right? I mean, it doesn't make sense, right? What does this make sense? It's not a binary number. Binary number 0 1 probably makes some sense, but if it is decimal 0 1, I mean, why would you pass 0 1? You either pass 1 or 1 0, right?
Another thing I want to ask, ma'am, like, then what is the sense of random if we are already fixing its
Yes,
value with some
that's
seed?
why it is not purely random, it's pseudo random. Okay.
Okay.
Yeah. Okay, next function is numpy.rand.randn. So there's a standard normal distribution. What is that? Anyone can tell me what is a standard normal distribution?
It's a normal distribution with mean 0 and
Mean
variance
zero
1.
variance is very
Mean
between
variance
0 and
1.
1.
Correct. So numpy.rand.randn generates a random number which comes from a normal distribution, standard normal distribution, which means a normal distribution with mean 0 and standard deviation 1. Okay. Every time you run it, you will get a number from that distribution. And if you want more numbers, see, if you simply run without any parameters, you'll get one number. If you pass some parameter, you'll get those number of random numbers, 10 random numbers you're getting. Similarly, if you pass two parameters, then it will give you a numpy array of that shape, 10 cross 2, which will contain the random numbers coming from that distribution, which is a standard normal distribution. Okay, this is numpy.rand.randn. Next one
Yeah,
is
so seed is confined to one cell. It is not affecting the.
yes.
Yeah.
Yes.
Sir, ma'am, what that second parameter, what does?
This one? Yeah, so if you're passing two parameters, that will be the shape of the resultant numpy array. Okay, which means 10 cross 2 will be the result, and 10 into 2 will be the number of random numbers that will be coming from the standard normal distribution.
So can we say that a data set with two features, right?
Yes, definitely. This is how we will be using this function in a while. Okay.
Yes.
Okay. Now, numpy.random.randint. If you are interested in integer random numbers, then we'll be using this. So when I put a bracket, that means it's optional. So let's say I pass two parameters. So first will be low, second will be high, 1 to 10. Okay. 10 will be inclusive here. So this is something that you may want to know. 10 will be inclusive here. It'll give you a random integer between 1 and 10. If you want multiple random numbers between 1 and 10, you can pass that to be the size. Now we are getting two random integers between 1 and 10. This is one function probably we might be needing. Another one is numpy.arange, probably you would have used so far. Here the parameters are start, stop, step. So you would have done in Python range function. It's similar to that only. That also had three parameters: start, stop, step. Okay. So start is optional, by default it is 0. Step is optional, by default it is 1. So if I pass 10, then between 0 and 9, it will generate numbers. So there's no randomness here. It just generates a list of numbers. Numpy.arange is a shortcut to create a numpy array that contains numbers in sequence from 0 to this number. I can explicitly pass the start. So in this case, 2 to 9. It's always 10 minus 1. It's always stop minus 1. Okay. By default, step is 1, which is, it's like this. We can change it. Now it will be start from 2. There will be step size of 2. We'll go up to 10 minus 1, which is 9. Okay, so this is numpy.arange. Next is numpy.concatenate. This is, as the name indicates, it's used to concatenate two numpy arrays. Okay, so the syntax is, let me create two numpy arrays first. Let's say This is one NumPy array. And then the next one. Now we want to concatenate. Okay. We'll write numpy.concatenate. In the parameters, it expects a kind of tuple of the NumPy arrays that you want to concatenate. Here we want to concatenate A1 and A2. So notice this. I'm passing an extra set of brackets. In that, I'm passing A1 and A2. So what is happening? The elements of A2 are getting concatenated with, at the end of A1 in that sequence. This is concatenation. Okay. These two were one-dimensional arrays, right? Sorry. What happens if they are two-dimensional arrays, right? In case of two-dimensional arrays, there's something that you should be aware of, and that is the shape of the two arrays. So that's something you might want to understand. So let me create two-dimensional arrays now. Now you may want to concatenate them probably row wise or column wise, right? In order to do that the same, you will need to pass an appropriate value of axis, and this is how you'll do. So numpy.concatenate. Again, you'll pass a tuple of the arrays that you want to concatenate. If I do simply like this, see what happens. Now let me print this. So this is how it is done. This is our first array, and this is our second array. By default, the axis, so this is one parameter, which is axis, that we should know how to use. After we pass this tuple of arrays to be concatenated, we should pass this axis value. By default, axis is 0 in case of concatenation. So if I even pass axis to be 0, it won't make any difference. So axis 0 means we want concatenation along 0th axis. In case of a 2D NumPy array, 0th axis refers to the rows, which means row-wise concatenation should happen. In case you want column-wise concatenation, you'll pass axis to be 1. In that case, you see what happened. 1, 2, 3, 4 was already like this, right? This was our first array, and then 5, 6, 7, 8 was the other array. So this column-wise concatenation happened, and that's how we got like this. So you should be aware of the axis whenever you are concatenating to make sure that you are doing the right concatenation.
Excuse me, ma'am. Hello. Yeah. How is this concatenation different from stacking different?
Yeah, you can use that also. You can use that also.
Okay,
you can achieve the same effect. Yes.
Okay. Thanks.
Yeah. Okay. Next is NumPy.
Ma'am, I had a very trivial question to ask at this point of time. While using concatenation function, while we are passing V1 and V2 as tuple, because the resultant answer is matrix only. So any reason, or it is just a part of syntax?
Your voice is echoing.
Am I audible now, ma'am?
Yes, go on.
You know, I said that while using concatenation function, why we are passing V1 and V2 as tuple, because the resultant answer is in matrix only.
The is going to be a NumPy array only.
Right. So any specific reason for that? It is just a part of its syntax.
Yeah, it is a syntax. So if you simply pass like this, you'll get an error because it won't understand what all to concatenate. So you have to pass in the form of I don't know. Let's try a list. I don't know. I've been using tuple only. Yeah, list also works. So basically, some collection you have to pass either a tuple or a list.
Thank you. Sorry.
Yeah, no problem. So next is numpy.linearalgebra.norm, which is used to get the norm of any vector. So I hope norm you are aware of. To get the length of any vector, you can use the norm. For example, let's say there's a vector. So let's use numpy.linearalgebra.norm on a vector. Let's say that contains 1, 1. Okay. So obviously, the length, this is 1, this is 1, this is your vector. So it gives us the length of this vector, which is going to be, square root 2, right, which is 1.414. Similarly, let's check 0, 5, let's say the length of this vector is going to be 5, right? So that's what we'll be getting. So numpy.linearalgebra.norm can be used to get the length of a vector. We can use this same function slightly differently to find the distance between two vectors, right? So this is something that we would be needing today in our implementation of k-means. So let's say you have two vectors. Okay. Yeah, so you have two vectors and then you want to find the distance between them. So you can write numpy.linearalgebra.norm of A minus B, right? So this will give you the distance between these two vectors. So A minus B is going to give you a vector, which is the difference vector. And then you're passing that inside this function that will give you the distance, or length of that vector is actually equal to the distance. So this is something we'll be using, because in k-means, what we would require is to find the distance of each data point from the mean. So for that purpose, we would be using from each data point, we want to find the distance. This distance, for this purpose, we'll be using numpy.linearalgebra.norm.
Ma'am, this is the L2 norm, right?
Yes, correct.
And I'm sorry to interrupt, but I have another question, that is, we just saw the function for the standard normal distribution where we generated the data set for that.
Sorry, what is the question? We generated standard normal distribution and then?
So can we use any other function where we want to give the mean and variance of the normal distribution as parameters?
Yes, so there are several functions. So in fact, there's numpy.random.normal where you can pass the mean and standard deviation explicitly. You can pass explicitly the mean and standard deviation, and you will get a normal distribution. But here, if you are interested in standard normal distribution, then we'll use random. Here also, you can pass mean 0 and standard deviation 1. So it'll give you the same result.
Okay, thank you.
Okay, so next function is numpy.argmin. I hope you are all aware of argmin. So let's say we have this array. This array, this small array, but no problem. So if you do numpy.min of A, what do you get? Tell me quickly. You'll get the minimum number. Okay, but on the other hand, if you do argmin, you'll get the index of that minimum element. Right? That's the difference between min and argmin. So argmin is something that we would be needing. Next one is appending. How can you append an element to an array? So numpy.append is what we can use. So let's say we have an array already. If you want to append some element, you can write numpy.append a comma whatever element you want to append. Let's say this. This is what will happen. 5 will be appended at the end. But you should note one thing, that numpy.append generates a view, which means it will show the output to you after appending, but it will not make changes in the original numpy array. It should remain the same. So if you want to make the changes reflect back in the original array, you might want to do A is equal to numpy.append. Okay, so this is how the changes will reflect back. Okay,
Here we have appended a single number. It could be append number digits.
Numpy dot append. So let's see if you can append more elements. Now let's see. We can check the syntax whether it allows multiple elements appending. Okay, it doesn't allow apparently. We start a loop, so it doesn't. One moment.
Ma'am, we can try np.extend instead.
No, that is in list. So, but this is working. But you see, this is working. There was an extra bracket there which was causing an error. So you can pass multiple elements apparently, as you can see.
It is working with square bracket also, ma'am.
Yeah, so we had a mismatch there. That was the problem there. Yeah, so you have to pass a collection basically. This collection could be tuple or list, anything. Okay, so next is the numpy.mean. As the name indicates, we will be, so because in k-means we have to find mean, so we'll be using this function. So again, there's one thing that you should be careful about, which is access. It's actually similar to what you have just now seen. So let's say, let's take a 2D array, and there it will make better sense. So we have this, right? Let me copy paste this. Yeah, let's say these two arrays are there, which are 2D arrays. Now you can use numpy dot mean. What do you want to find the mean of? Now we actually need one array only, right? If I do numpy dot mean, it flattens the 2D array or how many ever dimension array is. Flatten means it converts it into a 1D array. So this will become a 1D array with elements 1, 2, 3, 4. And the mean of that will be computed. That's what happens if you don't pass any value of access. If you want to find the mean row-wise or column-wise, you'll pass an appropriate value of access. So it works like this. Let's say this is your 2D array. If you pass access is equal to 0, then mean will be here, which means 1 plus 3, 4 divided by 2, which is 2. 2 plus 4 is 6 divided by 2, 3. So this will be your mean when access is equal to 0. And on the other hand, if you pass access to be 1, your means would be here, which means mean of 1 and 2 will come here, and mean of 3 and 4 will come here, like that. So which kind of mean you're interested in, you might want to mention that through access. In our case, as you know, when we have to compute cluster centers, we'll be interested in this mean. So we'll pass access to be 0. Okay. Let me show the difference. When we use access to be 1, we get the different means. Okay. Broadcast, I guess you people are aware of, but quickly let me do this. So let's say B1, we have already this one. And let's say I have another array. Let's say that's a 1D array with these elements. Now I can do B1 plus A. What will happen? Broadcast will happen. This will be 1, 1 will be added to this, and 1, 1 will be added to this. That's what will happen through broadcast. We might need it at one place. We'll talk about that then.
Ma'am, can you go again?
Yeah, so broadcast means so in general, it means some function being applied to every element or every row or every column, right? So that's the general.
I got it, ma'am. Thank you.
Yeah, okay. So next is, got it very quickly. Good. So next is.
Actually, I didn't, ma'am. Can you please that
okay.
broadcast part?
Yeah, so broadcast means, okay, we would have covered in first day. Anyway, so this is our B1, right? Or let's say A, this is our A. Now, if I do A plus 4, What happened? Quickly tell me.
And just 4 is added to both the numbers, like
Both the numbers. Why? Because I mean, I didn't explicitly mention that 4 should be added to each number, right? Did I mention that? I didn't. But by default, this is how it works in Numpy arrays. Any operation is applied to each element. That's generally that's the broad definition of broadcast. Okay. In our previous case, this 1D array got added this to this row as well as this row. That was the broadcast example there. Okay. Okay. Next is accessing array elements. How do you access array elements? Let's say you have A, right? No, which one? 1D array. Let's take an example of 1D array. Oh, let me create a better one. So let's say we have this array with some elements. Can somebody tell me how can I access second element of this array? Quickly tell me.
it's that A capital bracket and then
A1.
A1.
Like
Yes.
this?
Yes.
Okay. If I am interested in first 3 elements, what should I write here?
A colon
step
2.
one.
A0 colon 2 or A colon 2.
Yeah. 0, 1,
Sorry,
2.
it's
No,
A
3.
colon 3. Yes.
Yeah, because it is slicing. So last minus 1, right? Okay, this is the same as list. Now, let's say I'm interested in first, third, and fifth element. What should I do?
It's I think 4, 5.
What did you say?
Sorry.
First, third, and fifth element. I'm interested.
1:6 and increment.
Like this?
Then what's the
I'm interested in first, third, and fifth element.
Yes.
Is this fine?
1, 3, 5.
Is this fine? It's not fine. You have to pass.
You have to
a-
map 0, step size map.
Yeah, 0 to 4.
0,
we can-
1, 3, 5.
Not in this way, ma'am. We have to mention a step size.
No. Step size. Okay. Let's say first, third, and first, third, and seventh element. 0, 1, 2, 3, 4, 5, 6. There are only 6 index up to 6. So I'm not interested in elements at regular intervals. I might be interested in any element at any position, right? So these positions I'm mentioning. So all I want you to be careful about is you can't just pass, elements like this. That I'm interested in elements at index 1, 3, and 6. You can't do that. You have to pass a list of the indices whose elements you are interested in. So you might have observed an extra pair of brackets. This is again the same thing. It expects a kind of collection that contains all the indices which we want to access. Okay. That's one way of accessing elements. Is yet another way of accessing elements which we might be needing today. So, and that is, you can pass a list of booleans whose length is equal to the number of elements in the array. Wherever there is true, that element will be returned. Wherever there is false, that element will not be returned. For example, I can do like this. One, two, three, 4, 5, 6, 7 elements. One, two, three, 4, 5, 6. Now what happened? 1, 2, 3, 4, 5. There were 5 trues, so I get 5 elements. According to whichever index there was a true, we get that element. So first one has a true, we get that. Second, we get. Third, we don't get. Fourth, we get, like that. So that's another way of accessing elements selectively out of a given Numpy array. Okay. Next, let's now move on to k-means implementation.
I'm sorry to interrupt. So the ones where we have written false, those indices are not selected.
Right.
If we miss any true or false, like if we just keep none,
You
then
should get an error. Yeah, okay. You will get an error. The length should be
Then
equal
the
to the
first
number of
method
elements.
much more easier than this one.
It depends what is your scenario. Okay. It depends what is your scenario. Accordingly, you will use. Sometimes you won't have the indices like this. Sometimes you would have like this. as we will see today. Okay. Okay, data generation for k-means. So let's generate some data synthetically for k-means. So as we know, this is the kind of data that we have to generate. So let's generate some data where there are some clusters. So it becomes useful to apply k-means on that kind of data. We will be using numpy.random.randn. Let's generate some numbers from standard normal distribution. Yeah.
What exactly is the difference between random.random and the random.choice? Because both returns the integers, right?
Random doesn't return integers, it returns float values, and they are as per standard normal distribution.
Standard normal distribution. Random.choice and random.randint.
Random.randint. So there are several variants of random.choice. So let's say you want to generate, let's say you want to randomly choose from a particular array already. You can't use random.randint. You will use random.choice only, correct?
Okay. Does it return float values also? Can we use?
Yeah, if your array contains float values, it will return from that.
Okay. Okay. Thank you.
So numpy.random.random, as we know, will generate 10 cross 2 10 cross 2 array, which will contain the data from standard normal distribution. Now, let me do something. Let me apply.
Sorry to interrupt. This would be equivalent to 10 features and 2 data points.
Yes, 10 data points and 2 features.
So we're saying n by b.
Sorry?
So we're saying n by b.
N cross d. Yeah. So what is happening here? We are getting some 10 cross 2 matrix array getting generated here, and then we are applying broadcast here. So 10, 20 gets added everywhere, right? So this is the kind of data that gets generated. So now let me write some code and you'll be able to understand, because all the pieces we have individually seen. I'm just clubbing them up. So this is the code that I'm writing to generate the data set for k-means. I'm going to generate some 2000 data points, let's say. So we want data that has some 3 clusters, let's say. So for that purpose, I'm doing like this. Once I write this, you can ask me doubts. Although all the pieces we have already seen. Okay, this is the data of first cluster, then the data of second and third clusters. So I'm just changing, I'm just bringing in some randomness. You can have any numbers here to generate a different version of the data. Okay, so these are the data pertaining to each of the clusters. After that, let me concatenate. So all these functions I already showed you. Concatenate. Again, we have to concatenate these 3 things. We'll pass them in the form of a tuple which contains these 3 things. So this should be our data. Now, any doubt in this part? Any doubt in this part?
Yeah, hello, ma'am.
Yeah, go on.
Just I wish to ask a simple question. The thing that you have added on the top, right, in p.random.seed, this is equivalent to default RNG, right? Both does the same thing? Okay.
You can use that also, correct. So this is our data. So basically, I've generated, I want a data set that contains 3 clusters. So this is the data for first cluster and then second and third cluster, and then I'm concatenating them. This is our data, which is contained in capital X matrix. Okay. We can also visualize this data. So let me import matplotlib for that. So we can use plt.scatter for this. So what we want is there are two features in this data, right? We have already explicitly passed so that we can visualize. That's why we have taken two features. First feature we want on the x-axis. Second feature we want on the y-axis. So how can we extract from x? I hope you can do that. X, all rows, 0th column should be our x-axis, and from x, all rows, first column should be our y-axis. This is the kind of plot we want. So on the x-axis, we have first feature value, y-axis has the second feature value, and this is the data that we generated. Okay, this is data that has some good clusters.
Can you explain this one more time?
Matplotlib.
Yes, some scatter function. How did we get this?
Yeah, so plt.scatter expects the list that contains the x values of each data point, comma, the y values of each data point, right? So we are only doing one thing. So your x is this. Your x is 2000 cross 2, or maybe a little less than that, because we are using this kind of float function, right? Floor operator. So the point to note is that x has two features, which is two columns. You want that the first column should go on the x-axis of this plot, and the second column value should go on the y-axis of this plot. That is what we are extracting. This is how you do. From x, colon means all rows, comma, 0th column. Here you want the first column.
Got it.
Okay. Now this is our data. Now let's proceed with the steps of k-means. First step we have already discussed, initialize cluster centers. And we also discussed that they are done randomly. We also discussed that we have to initialize some value of k. Let's have k to be 3. Randomly, we have to choose the initial cluster centers. So we have 0 to 2000 or whatever, we have the data points. We want to choose 3 data points out of these randomly, and they should be our initial cluster centers, right? So let's code that. So let me first choose random indices by using numpy.random.randint, because we want indices. Indices are integers, so I'm using randint. It's from 0 to how much? Whatever is the number of elements in x, which we can get through x dot shape 0. You can also do len of x, that will also give you same thing, or x dot shape 0. How many random indices do we want? 3, because we have set k to be 3. So I can pass k here. Let's see what we are getting. So we are getting these 3 random indices, which means the data points.
We're saying 0 to x shape 0. So we're saying these are data points 0 to 2000.
Yes. Yeah, that's correct.
Okay, thank you.
So 0 to 2000, whatever are the data points, we want to choose 3 data points randomly. So we got the indices of those 3 data points, which we are randomly choosing. So what exactly will be the data points? Now we have to access them. And those data points will be the cluster centers. So let me have another variable that contains the initial cluster centers. The cluster centers is equal to x. Inside x, which data points? Random indices. Random indices. So basically here I'm passing the indices of the elements which I'm choosing to be cluster centers. So let's see what they are. So these indices that we had chosen, because each data point has 2 features, right? So this is the first data point that is chosen as the first cluster center randomly. This is the second data point chosen randomly to be the second initial cluster center, and this is the third initial cluster center. Okay, so these are the initial cluster centers that we have chosen. We can visualize them as well. So this is the visualization of the data that we have done, right? Let us also show the cluster centers there itself. So I'll add one more line here.
Ma'am, can you briefly explain again the last cell?
Which one? This one? This one? Hello?
Yes, ma'am. Yes, ma'am. Yes,
Yeah.
ma'am.
Yeah, so I told you how to access the different elements from a NumPy array, right? You can pass the indices. So here we had seen, right? We can pass the indices. So here we are passing the indices 1, 3, and 6. Same thing we are doing here, okay? Our indices are now kept in random indices. That's all we are doing, okay?
Okay.
Okay, now let's visualize the cluster centers by using same plt.scatter. Cluster centers, all rows, 0th column. Similarly, all rows, first column. And then let's have a different marker. I hope you have done these things from Matplotlib. If not, you might do soon. Marker we can mention so that we can identify that this is the cluster center. And what else we can use? We can give a size. Let's increase the size to be a huge number. So there are several parameters to plt.scatter. We're just using some of them. K stands for black color. Okay, we want to have cluster centers in different color. So you see, this is the initial setup. These are blue are the data points, and then pluses are our cluster centers, and they are randomly chosen, so they can be anywhere, right? Can anybody tell me what is the next step? For each data point,
we need to
assign their distance from the cluster centers, right? And yeah, like you said, we have to assign the cluster centers to each data point. How do we do that? For each data point, we'll find the distance of that data point from each of the 3 cluster centers, whichever is the nearest one, gets assigned to that data point. Okay, so this is our next step. How do we do it? I told you there is some Z that we'll be using. So let us keep track of the cluster centers assigned to each data point in this cluster indicator. So I'll create an empty numpy.array. This will be containing the cluster centers assigned to each data point. Now, how do we find the cluster centers? We have to check for each data point. So let me start a for loop there for each in X, let's say. What do we have to do for each data point in X? We have to find the distance of that data point from the cluster centers that we have already chosen, right? Let me create a variable. Let's say distance from each center. Okay. I've already told you how to find the distance between 2 NumPy arrays or vectors by using numpy.linearalgebra.norm, right? numpy.linearalgebra.norm we can use. Now here we want to find the distance between what and what. Can you tell me? One thing is each, right? One thing is each. And what is the second thing? Second thing is cluster centers, correct? So let me write that down. Cluster centers. We have to find the distance of each data point from each of the cluster centers. So we basically are interested in 3 things, 3 distances. The distance of each data point from first cluster center, second cluster center, and third cluster center. So I'm using list comprehension here. From Python, you would have done this. This I'm putting inside a list. So this list will contain the distance of each data point from first cluster center and second cluster center and third cluster center. Right? That's what this for loop is doing. We can print that out. Let's see what we are getting. So you see, this is what we are getting. For this data point, whatever that data point, let's choose one data point only. So let's say this one. For this data point, 3.14 is the distance from first cluster center, 2.5 from second, 3.8 from third. Now, what we discussed, whichever cluster center is the closest, that gets assigned to that data point. So here, for example, this is first, second, third. The distance from the second cluster center is the minimum, which means the second cluster center should get assigned to it, right? So how do we do that? We have done that function. Think and tell me.
We have to take the min along the columns.
Argmin, right? We are interested in argmin, right? We are interested in which cluster center is the closest. We are not interested in the distance. We are interested in which cluster center this data point is closest. So we are interested in the index. Yeah.
So this this dist from each center, this is this a list of lists? Or
this is a list of list, correct? Yeah.
Lists of okay.
Yes. Yeah. So
This will be for the 2000 data points.
Yes, correct. For each data point, we will have these distances. Okay. And then for each of these things, what do we have to do? We have to find which index contains the minimum value. For that, we'll use numpy.argmin. Okay. Distance from each center, right? Now, this chosen cluster should contain that cluster center, which is closest. So let's print that also. Chosen cluster.
Madam, do we need to provide access argument in?
Yes.
In which thing?
In np.argmin, do we need to provide access?
No, this is one thing only, right? What does distance from each cluster center contain? It only contains three things: one distance, second distance, third distance. There is no need for, there is only one axis. This is a one-dimensional thing. Okay.
But it is a list of lists, right, ma'am?
No, I printed one after the other. You see, there's a for loop. Inside for loop, that was getting printed again and again. The output of this thing is going to be a list containing three things. That's all. And then you apply argmin on this. This is a one-dimensional thing. So argmin, yeah. So I'm printing now the chosen cluster, right? This is what we're getting. We're getting either 0 or 1 or 2, right? Depending on whatever cluster center is the closest. 0, 1 or 2 values we are getting. Now these 0, 1 and 2 values are the cluster centers that are assigned to each data point. Let us store that in Z. Okay. So I'll write Z is equal to numpy dot append. What do I want to do? I want to append to Z what thing? Chosen cluster. Right? Z comma chosen cluster. This is what I want to append to Z. So this is all that we have to do to assign data points to different clusters. Now this is something that we would be needing later on as well. So what I'll do is I'll put this in the form of a function because this is something that will be needed again and again. So let me create a function to contain all this code. Define, let's say, let's call it identify cluster of each data point. Okay. And what inputs do we want? Obviously the X and obviously the K value. We're making it generalized by passing these parameters. Third thing we want to pass is cluster centers. Okay. So all this is going to be inside this function.
And if you would have written np.append z comma chosen cluster, so why do we
it won't have made changes in Z. I told you Z numpy.append generates a view.
Okay. Oh,
Return Z. Okay, this function. So this for loop gets over here. Now Z should be returned. So that's our function. Let's check whether it is working fine or not. So identify cluster of each data point. Want to pass X, K, cluster centers.
Isn't that function name is quite long?
Yeah, I explicitly gave it because later on we'll need that. So we wouldn't need to figure out what exactly this function does. So let's see. Okay, let's see if it works fine. Correct. So it is returning Z. This is what we need. Now we have done the first step. Okay. Now every data point has been assigned some cluster center. Let us also visualize it. So we have this code already. Let me copy paste it. Okay. We'll visualize these cluster centers. Now we have the cluster assignment information in Z. So there's a parameter in PLD.scatter that we can use, which is C for color. The color should be as per Z. So if Z value is different, there should be a different color and so on. So this is what we have. Depending on what our initial cluster centers were, which were bad actually. They were bad initial assignments, but that's done randomly. But we will run k-means and we hope to get a good solution. We'll see that. So as per the initial cluster centers, these are the these are the assignments that were made, right?
Could you please explain how did you change the color of the cluster?
Yeah, so C is equal to C stands for color. Okay, color is equal to Z. So I'm passing a list containing number of elements, which is equal to the number of elements in X. Okay.
Okay.
Z contains that 2000 elements. We know that, right? So if Z value changes, the color changes. This is how it works. PLT.scatter. Okay.
Okay. Okay.
Next is compute updated cluster centers. Now you see we have all these data points yellow, which means they belong to one cluster, right? And these green ones belong to one cluster. So now if we compute the mean of these clusters, these data points, probably this might shift here. This plus might shift somewhere here. This plus might shift somewhere here, right? So we'll have a displacement of the cluster centers. So for that, we need to compute the updated cluster centers. Okay. Now, how do we do that? Now you tell me if I do this, what might happen? Quickly tell me what might be the result.
It's a Boolean value.
One value.
Wherever
like
Z value is 0, it will become true.
Sorry?
Wherever Z has 0, it will
very
become
good,
true.
very good. So we will get an array of booleans, right? Wherever Z value is 0, in Z, wherever value is 0, we get a true, otherwise we get false. Similarly, wherever Z is 1, we get true, otherwise we get false, and so on. Now, this can be used for what purpose? Think and tell me. We can pass this inside what? Sorry, inside X, right?
To find those elements which have equal to this.
Correct. So if I do this, what will happen? We will get those
return
elements.
all the element which is equal to 0.
Correct. Now, I can generalize it because we want to do it for each cluster center. So I can use list comprehension like this for I in range K. So what will happen? I get one array, second array, third array inside this list. Okay. The first array contains all those data points which have been assigned to first cluster center and so on, right? Now, what we can do, what are we interested in? We are interested in finding the means. So I can apply here numpy dot mean. I have to find numpy of mean of these data points with an axis to be 0 because I want row wise mean, right? We discussed that. Now what happened? We applied that mean, okay? And this is the updated first cluster center, updated second cluster center, updated third cluster center, right? So these are the 3 updated means. This is what we wanted, right? So let me put this in the form of a function because this is also a step that we'll be needing again and again. Let me call it compute cluster centers, and inputs will be X, and what else? Z and K. These are the inputs that we want. Now, whatever results we get, let's call them cluster centers because this function should return them. Let's return this, return cluster centers. Now, one more thing that we might want to do, because we'll pass these cluster centers, we'll be using these cluster centers, and everything is in the form of NumPy arrays, whereas this is going to be in the form of a list. You see, this is a list of arrays. Let's convert this into NumPy.array. So everything in the form of NumPy array so that we can apply all these array functions. So let's not have this in the form of a list. Okay, this is our function. Let's check whether it is working fine or not. This thing is returning cluster centers. So let's check this. And let me then print that. All right, so we are getting these three cluster centers. This is first updated cluster center, second and third, right? So far, what have we done? We did the initialization of cluster centers. This is our data. We did the initialization of cluster centers, 3 randomly chosen. Then we, based on those initial cluster centers, we assign each, we did the assignment step. Assign each data point to some cluster center. When we assign that, this is what we got. And then after that, we can find the updated cluster centers. This is what we are doing. Now, you know that these 2 steps have to be executed again and again. Now that you have found the updated cluster centers, what is the next step? Once again, for each data point, you'll check which cluster center is closer. If some data point is not happy, it will be reassigned. So that's what we have to do iteratively. Okay. So now we will be basically calling all these functions, 2 functions that we have created again and again. How many times? We can decide that. Let's say, let's run it for 10 times. You can change this. For now, let's see whether we are able to get good clusters in 10 iterations. First step, after getting new cluster centers, what is the next step? We have to do the assignment. I mean, we have to find the cluster centers for each data point, right? So I'll use this function, which we have already created. And this function returns an updated value of Z. So I'm fetching that. When we get an updated reassignment, we can also display it using Matplotlib. It will be good to keep checking what happens in each iteration. So let me visualize things as well. In order to show what happens in each iteration, we have to explicitly write plt.show. After seeing that new assignment, we can once again find the updated cluster centers. So we can use this function compute cluster centers. Compute cluster centers. And what does it return? It returns cluster centers. Let's also print cluster centers. Okay, so basically we are performing this step and then we are visualizing, then we are performing this step. And this goes on for 10 times. Let's see what happens.
Sorry to interrupt. For I in range 10 indicates what?
We are performing 10 iterations. You can change it. Generally, k-means converges fast, but if it doesn't, you can increase the number of iterations. This is a hyperparameter. How many times you want to run this? You want to set an upper limit. So this is what is happening, you see. This is what is happening in different iterations. This is in the second iteration. Cluster centers got moved, as I told you earlier. These are the updated cluster centers. And then in the next iteration, some more movement happened. This is third iteration, fourth, fifth iterations. You see how the data points are getting reassigned. and in some 6-7 iterations, we are getting this kind of configuration, and you see in some 6-7 iterations, it is able to get good clusters. So you see how the cluster centers are moving from one point to the other, right? Now you ask me your doubts.
And instead of taking 3 cluster center, we can take as many cluster centers.
We can take as many cluster centers as possible. So this was data that we had ourselves created. So we knew that we have created 3 clusters in the data, right? But generally, obviously, in any given data, which we cannot even visualize, we will not be able to make out how many clusters there are. So we generally try out different values of K. That's what we do. Probably you will do it in MLP. So K is a hyperparameter in K-means, which means this is something that has to be tuned through several techniques. So we try out different values of K, and whichever gives the least loss is the configuration that is kept. Is that clear?
Yes, ma'am.
Excuse me, ma'am. So I don't really have a doubt per se, but this step that you did in the last step, so basically going over each iteration of the algorithm and then plotting the graph, is there some kind of library or package that could turn this into a animation kind of a stuff?
Library. So sklearn already has this implemented. Are you talking about that or this?
No, so no, it's like.
Okay, that animation you're saying. So
yeah.
You can actually GIF files you can create, and you can keep all these plots somewhere in a folder, and then from them in sequence you can create GIF file that can show you how your cluster centers move from one point to the other. That definitely that is doable. We can do that.
Okay. And just one thing, is this session over, or are you going to cover something extra today?
Yeah, we have to cover Perceptron. That's why I have to go a little fast, because we have to cover these 2 topics today.
Okay. Thanks. Yeah, that's it.
Ma'am, here we have identified the clusters for each of these data points. What is the final output of which data point is in which cluster?
Yeah, so Z will contain the final details, right? Z is getting changed in each iteration, correct?
We just need to print the final Z.
Yes, Z will contain the final cluster assignment details.
And what about the loss? I mean, how do we identify the loss here?
You can identify the loss. So what is the loss in K-means? Anybody can tell me? The distance. So basically, you can't say loss per se. The objective function. So the objective function in K-means is to minimize the distance of each data point from the cluster center. So to find that, what you will do, the cluster details are present in Z. For each data point, you can find the distance of that data point from the cluster center that it has been assigned to, correct? Using numpy.lin algebra.norm, you can find the distance. You can sum this up you can just start a loop. You can sum this up for each data point, and that will be the value of the objective function. So probably if you can actually
we have to create a new function.
Yes,
for the objective function.
Correct. So for this particular configuration, there will be some value of objective function which will be high, and then gradually as you keep moving on, the value of objective function will keep reducing. You might want to take this as a challenge and update this particular code to incorporate that also and keep printing that also. Okay.
Here you took 10 iterations, but how do we really come?
Yeah, that's a hyperparameter. That's a hyperparameter. So generally, it depends on the data set. So we generally try out different values of this. Something like max iter or something. I don't know, you people are through with the MLP or not. So see, we know that K-means converges, but still, if you want to give an upper limit of the number of iterations that should be tried, let's say you are short on time and you want to keep control of how many iterations run, you can give a parameter, and that parameter is there in every implementation that we do. So in this implementation, we are using this to be 10, but you can always vary it. In any implementation of k-means,
Sort
this
of
will be
like
a
a
parameter.
trial and error to see which one really works.
So hyperparameters are, I mean, that's not how we say trial and error. So given any data set, we try out different values, whichever gives the least loss is the final one. Okay.
Ma'am, can't we put a condition in the for loop that if all points are happy with their respective cluster center, then then we can stop the iteration.
Yeah, you can. So definitely you can do that. So like I just now explained that you can compute the value of objective function, right? You can keep track of this objective function value across each iteration. And when you see that this objective function value is not reducing, okay, or this objective function value that is reducing is very small, you can stop it. You can put a break there. Okay, the same thing we do in gradient descent also, right? SGD regressor, I mean gradient descent, we also do something like that. Yeah.
Okay,
yes, you can do that. Okay, I
Ma'am,
hope it was clear. Yeah.
Somewhere I lost you. I'm not getting the correct output. This Collider notebook is not like updated in the drive. Like it's not the.
In the drive, you would have questions, right? Not this code. This code I'll probably do it after the session.
Okay.
Yeah.
No. The drive, the collab file is just blank. So
is that blank? Whatever I copied, there might be some questions there, right?
No. Like I think
Code is
others
not
can
there.
also.
It is all questions are there, ma'am. Actually,
questions are there, no?
In past session, what sir are coding, they are just get updated instantly over that.
Oh, they were working in that one, is it?
Yes, actually.
Okay, so after the session I'll do it. So whatever you have lost upon, you can get back there. Okay.
Oh, okay, ma'am. Thank you.
Okay, so we have to now start Perceptron. Let's take a break of, let's say, 7 minutes. We'll start at 9:45. Is that okay, everyone?
Sure,
Yes, ma'am, it's okay.
Sure, ma'am.
Okay, so we'll 9:45 sharp we'll start Perceptron.
Thank you, ma'am.
See you. Okay, welcome back, everyone. Let's resume. Okay, can somebody confirm again whether my screen is visible and I'm audible?
Yes, ma'am.
Okay, thanks. All right, so now.
7 years got over so quickly.
Sorry?
7 years got over so quickly.
Yeah, exactly. Yeah. Okay, so Perceptron. Okay. This is, as we know, is a supervised ML technique. Perceptron is one of the oldest techniques for classification, and it follows a very simple algorithm. It has been proved that perceptron converges. Again, like k-means, we have a proof that perceptron converges as well. This is also an iterative algorithm, which we will see. One important thing about perceptron is that it gives very good results on data, which is linearly separable. On the other hand, if the data is not linearly separable, this algorithm doesn't produce good results, although that is true for any other algorithm as well. But in case of perceptron, it is able to come up with zero loss if the data is linearly separable, and that too by using a very simple technique, which is there in its algorithm, which we will see. So getting back to linear separability, this data that you see is linearly separable, which means we can come up with a decision boundary such that on one side of it, we have one kind of data points, and on the other side of it, we have other kind of data points. So we can write it like this. Let's say we represent one class by +1, another class by -1. This W transpose X is the equation of this line, right? W transpose X, I hope you know what that means, right? W naught X1 plus W2, W naught X naught, W1 X1 plus W2 X2, and so on, depending on how many features are there. So this is what is W transpose X precisely, right? So wherever W transpose X is greater than or equal to 0, we get the positive class. Wherever it is less than 0, we get the negative class. So if this is possible, then your data is linearly separable. And if your data is linearly separable, perceptron can give us a decision boundary, which gives us zero loss, which means all the data points are correctly classified. On the other hand, if the data is not linearly separable, which means you have some data points of the other type on the other side, this is non-linearly separable. In this case, perceptron will not converge and it will keep fluctuating. The loss will keep fluctuating. So if the data is linearly separable, perceptron is one of the best algorithms and quite fast as well, quite simple as well. Now, what is the algorithm that we have to implement today? Let's understand how it works. Before we get into details, let me first give you a background, an example, and then we'll go over the algorithm so that we can quickly understand. The data points are given. Let's call them these. We will start with some value of W. We'll call it W naught, which means some initialization for W we are going to do. So if there are two features, this will have two. So this will be a zero vector. That's what we will initialize W to be. If there are two features, this W will have two zeros. If there are three features, W will have three zeros, and so on. We follow the data points in some sequence. This is something to note. We follow the data points in some sequence. This is something we decide already. Let's say we're going to follow this sequence, which means first we'll check X1, then we'll check X2, then we'll check X3, and so on. Now, we will apply this W to this X1, which means we'll compute W transpose X1 with this W value. What will be the prediction? If W transpose X1 is greater than equal to 0 and the class of X1 is +1, which means this W is able to give correct classification for X1, right? I repeat, with this W value, we will compute W transpose X1. If W transpose X1 is coming out to be greater than equal to 0 and the class of X1 is also positive, getting back to this, right? This is positive, this is greater than equal to, so this is fine. And this is negative, this is less than 0, that should hold. Now here, it is holding, which means this W value is able to classify X1 correctly, which means we are good. We can move on with the same value of W, which is W0. When we reach this data point, we will compute W transpose X2. If W transpose X2 is able to correctly classify X2, what does that mean? Let's say W transpose X2 again comes out to be greater than equal to 0 and the class is +1, or it could also be W transpose X2 is less than 0 and this class is -1. Again, this is matching. If it is matching, which means we are good, we will proceed to the next data point. In case it is not matching, which means, let's say W transpose X2 is giving us greater than equal to 0 and the class is -1. This is not matching, right? The signs are not matching. Here the sign is negative, here the sign is positive. They are not matching. If that happens, what do? We apply an update rule. Like there's an update rule in gradient descent, there's an update rule in perceptron also. What is the update rule in perceptron?
WT plus 1 is equals to WT plus XY.
Correct. W transpose X plus XY. This is our W new. So let's call it W new and let's call it W old, right? Yeah. This particular thing. So let's call it W new, let's call it W old, and what we add is X into Y, right? You can put the subscript Xi, Yi, because we are dealing with ith data point. So this is the update rule, okay? If we get a mismatch, we will update W. Let's say we had gotten a mismatch with X2, so we will update this W, which earlier was W0. Let's say now it becomes W1. Now, with this W1, we will move to X3. We will check whether X3 is being correctly classified. If yes, we will move to X4 with the same value of W. Now we will check whether W1 is able to correctly classify X4. If yes, we will move to X5 with the same value of W. If not, once again, we will apply update rule. Once we apply update rule, we will get another value of W. Let's call it W2. Okay, so we will move to X5 with W2. We will check X5 with W2. If it is able to correctly classify, we move to X6 with same W2. This is called one iteration or one epoch. In this epoch, some mistakes happened. What is a mistake? Which means, mistake means we were not able to correctly classify the data point given the latest value of W. That's a mistake. We can keep track of how many mistakes happened in this iteration. For example, let's say 2 mistakes happened in this iteration. By the end of this, we have some value of W. Now, what we will do, we will move with this value of W once again at the start. Once again, we will check whether W2 is able to correctly classify X1 now, because now we have an updated W, right? If it is able to correctly classify, we move to X2 with W2. If not, we will update, all right? We will check with that value of W with X2. Let's say it is not able to correctly classify. Once again, we will apply update rule. And let's say we get a W3. We move to next data point with W3. Let's say it is correctly classified. We move. Let's say correctly classify. We move. Let's say correctly classify. We move. So by now we have W3. Number of mistakes that happened in this iteration are 1. Now, once again, we go to the beginning with this value of W3. We check X1 correctly classify. Yes. Let's say yes. We move on. Correctly classify. Correctly classified. Let's say all the data points in this iteration are correctly classified, giving the number of mistakes to be 0. When the number of mistakes comes out to be 0, we can stop. Okay, that's when we can stop. So this latest value of W is the value of W that will give us this line W transpose X, which will be able to correctly classify the given data points. Now, given this understanding, let's quickly go over this algorithm. This is our data, X and Y. Y's are +1 or -1. We initialize W, let's call it W0. All zeros. Number of zeros will be equal to the number of features, which is D. Until convergence. So here convergence is, I told you, when the number of mistakes is 0 in a particular iteration. That's when the algorithm is said to be converged. What are we doing in each iteration? Pick an XY pair. So this is little informally written, but I told you, we follow some sequence. Let's say this sequence. This is something that we will define already, and we'll keep following this sequence only. So we'll pick one pair in this sequence. We will check whether W transpose X, this WT value of weight when used in W transpose X, is it able to correctly classify that data point? How do we check that? We check the sign. If the sign matches with YI, that means it's correctly classified. If it does, we don't do anything. If it doesn't, we apply the update rule. And you know this update rule, new W is equal to old W plus XY. That is all. This is the algorithm of Perceptron, which we are going to code. Any doubts so far?
Ma'am, what is the significance of W star? Like
Sorry, which one? W what?
W star, something we read in like we read in MLT section. It's a W star, which is
okay.
Optimum solution.
Proof.
optimum solution.
You're talking about the proof, is it?
No, ma'am. The optimum solution, like.
Okay, probably they're calling W star to be the final W, the optimal value. I'll have to check the lecture again to be able to correctly say what W star is. I think the last W, right? The latest one.
Yes, ma'am.
Yeah, correct.
No, actually, it is some kind of average of all the Ws or.
No. It's not average. No. Are you sure?
Okay. Like I'm not confirm.
No. I don't think it can be average. It is it should be the latest. We don't find average. No.
That's a final W.
Okay. All right. So let's go on with the code. Any doubts before that? Okay. I hope it's clear. It's a simple algorithm that we have to implement. Let's first of all import two basic libraries, Numpy and which one? Matplotlib. Okay. Matplotlib.pyplot as ELT. Okay. Now we need a classification data set, right? So we can generate that manually using Numpy like we did earlier. But I thought I'll introduce you to a new way of generating data. You might do it in MLP actually later on. So I'm actually using sklearn here. In sklearn, there is a submodule data sets, and inside that there is a class make underscore classification, which is used to generate classification data set. You shouldn't worry about these parameters. I'll just introduce you to them. That's all. Don't worry much about these parameters. You might do this later. All that we should know is that this is generating a classification data set, and I'll visualize that also to show you. So we are generating 50 samples, which means 50 data points, so that we can visualize. We are taking 2 features so that the data is in 2D, and both these features we want to be informative, which means both of these features should be good. In real world, there are some features which are not good as in they might be linear combinations of each other which are not good, or in other words you can say redundant. We don't want any redundant features given that we have only 2 features. We can have this number of clusters per class. So we want data belonging to 2 classes, right? Classification data set. So we want 1 cluster per class. This is not that important because by default we will get, this is one data, one class, this is another class, like that. There's 1 cluster here, 1 cluster here. You can increase it if you want data to be a little spread out. So these are just some parameters to control. Don't worry much about them. Then this is to introduce noise in the data. I don't want any noise in the data because we want linearly separable data. And I want to mention some separability between the classes so that we can make sure that it is actually linearly separable and some random state for reproducibility. That's all we are doing. This is given to you.
Is the class separator something like the gamma margin?
Similar to that. Yes. So I am explicitly giving a high value. The default value is, I think, 1. I'm giving a 3 value. Okay. I'll show you when I visualize it. So this is our data, capital X and small y. If I want to see how many samples there are, quickly tell me what should I write. If I want to check how many samples are there in this data,
shape.
X dot shape 0. Right, will give us the number of data points, and then similarly X dot shape 1 will give us the number of features. Okay, so which is 2,
I'm
right?
sorry to interrupt. There's some confusion that is going on in my mind. Throughout the MLT course, we were focusing on data sets where the matrices were D cross N, but whenever we are doing the coding part of it, we're looking at only N cross D.
Correct.
Is there
Correct.
a reason behind it?
So in practice, the data that we get is actually N cross D. Okay. But in all theoretical contexts, which is MLT also, we tend to take the given matrix capital X to be D cross N. Okay. And then you do X transpose to get N cross D, right?
Okay.
Right. So that's how we do. I mean, in most theoretical contexts. So in fact, in different books, you might get it differently also. So you might want to make sure what their X is. Okay.
Okay.
But in all practical purposes, for example, if let's say, imagine a CSV. In CSV, generally how the data is organized, tell me. So let's say
comma separated.
N cross D.
Correct, N cross D.
So row wise data.
Yeah, row wise. So in all practical purposes, and hence in MLP, we take it to be N cross D. Is that clear?
Yes, thank you.
Yeah. Okay. So as I told you, in Perceptron, generally we take positive and negative classes to be +1 and -1. So in the given data, we would have the classes to be 0 and 1. Let's see that also. Let's see what our Y looks like. Y looks like this 0 and 1. So in fact, you can go with 0 and 1, but if you want to apply an equation like this, where, if Y is +1, you use plus here. If Y is minus, you use minus here. In order to have such a consolidated equation, we would want the Y to be +1 and -1. If you want to keep your data to be 1 and 0, you will have to alter this equation accordingly. Okay, so for now, let's go with this equation, which expects Y to be +1 and -1. So let me replace all zeros in Y with -1. Okay, how I can do that? Several ways to do that. So inside Y, wherever Y is equal to 0, let me make that -1. Okay. So let's see what is my Y. This is now our y, which contains only one, positive +1 or -1. If you want to see unique classes, I hope you know numpy dot unique is what you can do, right? Numpy dot unique of y will tell you how many unique classes are there, -1 +1. Let's plot the data. Similar ways, the way we had done earlier also. PLT dot scatter we can use. Once again, the first feature we want on the x-axis, second feature on the y-axis. And let's plot the data points belonging to each class in different colors. So PLT dot scatter, let's use that. X all rows, 0th column. X all rows, first column. And then color should be as per y. If y changes, color should change. Okay, this is the kind of data that we generated. As we can see, this is quite well separated. That is because we had given this parameter. We can control the kind of data that we want to generate. Class separator, I had given explicitly a high value to make sure that they are far apart so that we can apply something like Perceptron. Okay.
How are the values of X distributed? I mean, is there any distribution for that? Or is it completely random?
It is random actually, but definitely some technique or some procedure is followed by make underscore classification. If you want to get into the details of that, definitely you can check the source code that is available on GitHub or in sklearn documentation itself. You can check it there. Some technique is followed, but it is random only. Okay. Given these parameters values are followed, but then it is random. If you change this random state, you will get different random numbers, but then they will follow these parameters. Okay, so this is our data. Now let's proceed with Perceptron implementation.
Ma'am, what is that y equals to c doing in
C is equal to y?
Yeah, this one.
C for color. The color should be as per y value.
Okay.
So to start with, we have to have some w, weight vector, initial weight vector, which will be all 0. To have an all 0 vector in NumPy, what function can we use? Tell me.
NP dot zeros.
Yeah, now NP dot 0. Now, what should be the dimension of this? Tell me quickly.
2, right?
Shape 0. Yeah, it should be 2. You can write 2 or you can simply, not 0, not shape 0. It's n cross d. You want d. So x dot shape 1, right? You want 2 zeros, right? Because the number of features are 2. D is 2 here. So you will have x dot shape 1. Okay. Now, after getting w, what do we do? I told you this complete procedure. For each data point, we will check whether this w is able to correctly classify or not. If yes, we will move on to the next data point. If not, we will apply the update rule, right? That's all we have to do. So we're doing it step by step. Let's read what the question states. Iterate over each data point in X one by one. For each data point, compute the value of W transpose X. If W transpose X is greater than or equal to 0, predict a positive class, else predict the negative class. We'll do the comparison in a while, but for now, we will see what W's are giving, what W is giving for each data point. Okay, we'll do the update in a while, in a moment. Okay. Just continue from here. This is our W. For I in range, len of X you can write, or you can write X dot shape 0 also. One and same thing. What do we do with each data point? We have to compute
dot product.
Correct. W transpose X also you can do, or you can find dot product. One will give you the same thing. Let's call it Y pred, which means the predicted value of Y. So Y pred is equal to 1 if W transpose X W transpose, how do you find? W dot T will give you W transpose. And then you do the matrix multiplication. For that, you use add the root. I think you would have done that yesterday. W transpose X, Xi. So Xi will give us the ith data point, right? With the I data point, we are multiplying W. So W transpose Xi. If it is greater than or equal to 0, then Y pred is 1. Else Y pred is equal to -1, right? Let's print also. Let's see what is the actual Y value and what is the predicted Y value. So actual Y.
Ma'am, W transpose Xi should be dot product, right?
See, one and same thing, right? W transpose.
Okay, so it's only one element, yeah.
One element, yeah.
Right. Okay.
Yeah. So we are printing the actual Y value and the predicted Y value. So let's see what we get. This is what we get. So here, actual and predicted is matching here so far. Here, the actual is -1 and predicted is 1. This is and so on. You can check out. So these are the predictions coming from the initial W that we set to be 0, 0. We have not applied any update rule so far, which is what we have to do. So we're going step by step. So far, we have understood how to predict, how to see what value is being predicted by the given W. If prediction does not match the actual class label, update the weight vector as per the update rule. This rule. Okay. So what do we do now? If Y pred is the predicted value, if it is not equal to the actual value, what is the actual value? Contained in Yi. If it is not matching, what do? We apply the update rule. And how do we do that? W is equal to W plus X into Y, right? X into Y. So how do we do that X into Y? So Y is actually a scalar. It is either +1 or -1, right? And X is a one-dimensional vector. So we can simply write X into Y. How can we write? X of I into Yi, Y of I. Okay, so this is our update rule. W new is equal to W old plus X into Y. We are dealing with ith data point right now in this iteration. So we'll write Xi, Yi. This should be our updated Y value. Okay.
Sorry to interrupt. Yi is a scalar. That's why we don't have to do dot product, right?
Yes. It's just a scalar. Yeah. It's a scalar multiplied by a vector.
Ma'am, also instead of -1, we can also use 0, right? To denote the negative class. Is it okay to use 0?
See, if you use 0 here, what will your update rule become? W is equal to W, right?
Updated.
Right? So you will have to accordingly update this also, right?
Okay.
So
is it the
what you
reason
want to do? Yeah, this is the reason. So you can write it concisely, right? This equation works even if your actual Y is positive, or if it is negative. This equation works. Kind of you write a short form, but nobody is stopping you to continue using 0 and 1 as well. You can do that, but then you'll have to write two if else, two conditions separately. If your Yi is equal to 1, then you do W is equal to W plus Xi. If your Y is equal to 0, then you write W is equal to W minus Xi. That is something you will have to explicitly write. Are you getting?
Yeah.
Okay, next one. Keep track of the total number of mistakes made by the algorithm. Now we are updating the W's, right? That's we have done till that point. Now let's keep track of the total number of mistakes also. Let me copy paste this code and proceed. Let me have a variable total mistakes is equal to 0 initially. And then the moment there is a mismatch, that means that's a mistake. And hence we have updated W. That point, let's increment total mistakes plus equal to 1. Okay. So total mistakes we are incrementing by 1. And once we are
Why
done
do we
this,
need to keep a track of the mistakes?
I told you, right? So I was telling you this. In each iteration, you want to keep track of the number of mistakes so that you can stop, right? When there are no mistakes that are happening in any iteration, you can stop, which means you have converged. Okay. So total mistakes we can print after we are done with this one iteration. Please note that we have run only one iteration through the data so far. Okay, so we made 2 mistakes in the first iteration, and hence we updated the W twice. Okay.
Ma'am, hello ma'am. Ma'am, total mistakes is basically number of iterations, no?
No. Total mistakes is, there can be multiple mistakes that can happen in an iteration. Okay. An iteration is one pass through the entire data. We will have several passes through the entire data, like I was telling you here, right? This is one pass. This is one pass. And we got 2 mistakes here. Then next pass, this is next pass, we got 1 mistake. Then next pass, we got 0 mistakes. Okay. Is that clear now?
Okay.
Okay, so so far we ran only one iteration. Let's do it for several iterations. Okay. We can stop if there are no weight updates. And when there will be no weight updates, when there are no mistakes. So for that, we are keeping track of these mistakes, right? So let me copy paste this code and we will update it to run it for several iterations. This is our weight and then total mistakes 0. Let me call it epochs. You can have iterations, any name you can give. Let's say we want to run up to 10 iterations. These are total mistakes, please note. Let's keep track of how many mistakes happen in each iteration. You can use any data structure for that. Let me use a dictionary for that so that I can store like this. In first iteration, let's say 2 mistakes. In second iteration, let's say 1 mistake. In third iteration, let's say 0 mistake. And so on. When there are 0 mistakes, we can actually stop. So to keep track of this, you can use anything. You can use a list if that works with you. I prefer using a dictionary here. Let me call it weight updates per epoch. I'll just create an empty dictionary here. And now we have to do all this for several number of epochs. So I'll start another for loop here for epoch in range epochs, which is 10. Okay. What do we have to do in each of these epochs? Firstly, this should be a part of this for loop. And let us also print which epoch we are inside. So let me add print epoch number. Basically, we want to write epoch. This will tell us in which epoch we are right now. And I should initialize number of weight updates. The moment we are starting with an epoch means iteration, don't get confused with that. So the moment we are starting with an iteration, I should mention that there are 0 updates so far. I hope you know how to work with dictionaries, so that's all I'm doing. When we do this, epoch comma 0, epoch colon 0, that gets added. Epoch number comma colon 0, that gets added in the dictionary. Like this gets added in the dictionary.
Maybe do a +1.
Yeah, later on when we make an update, which means some mistake happened, we will update it. We will add it by 1. We'll increment it by 1. So where do we have to do that? Let's see. This is going over each data point. This is fine. And then if this doesn't match, then we are applying this thing. Total mistakes we are incrementing by 1. apart from that, we have to increment this, like somebody just now mentioned. We have to increment this. How do we do that? Plus equal to 1. I hope you know how to work with dictionaries. So we're just incrementing that value by 1. Okay. Now, if in a particular iteration, no weight update happened, we would want to come out. We would want to stop. We can actually go on, no problem, but doesn't make sense. So let's add a break condition here. Once this for loop gets over, right? Where do we add it? Outside this for loop. Let's add if weight updates per epoch is equal to 0, which means no updates happen in a particular update. That means we have kind of converged. Oh, sorry, I think did anybody ask a question in meanwhile? I think I couldn't hear that. Yeah. So if no updates happen in a particular epoch, we would want to break. And when we come out, let us print total mistakes. And yeah, this is outside for loop. Let us also print our dictionary. Dictionary is this. This is our dictionary. Let us print that also. We can also print the value of W, which is the latest weight vector that will be contained in W. These 3 things we want to print. Okay, so let's go over. We are just initializing W. Total mistake 0. Total mistakes is total mistakes so far. Okay, 10 epochs we are running this. We are keeping track of the number of updates made in each epoch. This is going over each epoch, each iteration. In each iteration, we are going over the data. Okay, in each iteration, we are going over all the data. So this is fine. And then if there is a mismatch, we update. We add 1 to total mistakes. We add 1 to weight updates in that epoch. After we come out of this for loop, we are checking this. This seems fine. Okay, let's run this. Okay, this is what we are getting. In 0, this is 0th epoch, and then first epoch. In first epoch, this is our dictionary. Just focus on this. 0th epoch, 2 mistakes happened. First epoch, no mistake happened. 0 mistakes happened, which means no update needed to be applied, which means we are converged in second iteration itself. This is our final weight vector. Okay. So within 2 iterations, in the second iteration itself, we converged. So this is Perceptron applied to the data that we generated. As you know, as you can see, this is converged much faster. We can also visualize it. We can plot this. So basically, we can plot the data, and the decision boundary also we can plot, given that we have gotten this W. Right? We've gotten this W. So decision boundary, as you might know, is perpendicular to the weight vector. So let's say this is one kind of data, and then this is another kind of data, and then we've gotten the W, right? Probably, let's say W is like this. We got this W from our code, and the decision boundary will be perpendicular to the weight vector. How do we get that? So firstly, we'll have to plot this W. We'll plot this. So in matplotlib, there is plt.quiver. I don't know you've been introduced to this earlier or not. So quiver is a function that we can use to plot an arrow, which is what we need for the vector. So we will use that. Now we want a perpendicular line to it. So what we can do is there is a way that you can get a perpendicular vector to a given vector. So let's say there's a vector a1, a2. This is a vector. If you want to get a perpendicular vector to this vector, you can apply a transformation, and the result of that transformation will be this minus a2, a1. You basically interchange an a1 and a2, and you make this minus negative. This will be a vector.
Could you please repeat the last part about this vector and transformation?
Yeah, I'm saying this is from mathematics, linear algebra. If there is a vector and you want to get a perpendicular vector to that, you can actually apply a transformation matrix. So transformation matrix will be 0, -1, 1, 0. This will be transformation matrix. When you apply this transformation matrix to the given vector, you will get this vector. You may not need to worry about this. Quickly, you can do this a1, a2, interchange the place of a1, a2, and then negate this thing, first element. So this will give you a counterclockwise perpendicular vector. This one, this will be this one. There is also one more this vector also. This is a clockwise perpendicular vector. If you want to get this is just the negation of this one. As you can see, this vector is the negation of this one. So if you want to get that, you can get that a2 minus a1, just negate this vector. So this information you can use to plot the vector and the decision boundary.
And if W is having more than 2 features, then how to get that transformation matrix?
Yeah, accordingly, the transformation matrix will have 3 components. We can see the transformation matrix in that case. Okay, so there'll be 3 components in the transformation matrix, and accordingly we can see what will be the resultant perpendicular vector. Yeah, so this is only in the case of 2D vector. Okay, we can check out for other dimensions. Okay, let's first plot the data and the decision boundary. For data, let me just use this, and then we will plot the decision boundary and the weight vector. This one. Now let's use plt dot quiver. Now the parameters are the starting points of the vector, which are origin 0, 0, and then W0 will contain the first component of W, and then W1 will contain the second component of W. There is also a parameter scale. So this might be a small vector. Let's increase its size so that it is visible clearly. There's also an option to change the color. Let's see what kind of output we get. This is the kind of thing that we are getting. This is our weight vector. Now to print, to display the decision boundary, we will use quiver only again. So 0, 0 to, like I said, W1 and negate it, and then W0. So instead of W0, W1, I'm writing minus W1 and W0. I'm interchanging and putting a minus sign here. And then let me change the color. Let's say, because this is going to be the decision boundary. And then to get the other direction perpendicular vector, let me have a negation of the above one, W0 minus. Okay, let's see. This is the kind of thing that we're getting. So this is going in the above area, which is not visible. So we can use plt dot ylim. We have plt dot xlim, ylim to limit how much we want to display. So ylim, let's start from -4 to 4. -4 to 4. Let's see. Okay, so this is what we are getting. If you don't see, this is decision boundary, so they are not supposed to be arrays, arrows over here, right? So we can suppress them. There are more parameters in plt dot quiver. For example, head axis length. You can all see all this in the documentation of quiver. We don't want to display this arrow. Head length also, let's make it 0. Okay, so this thing, let's see. This is our decision boundary. If you want to further elongate it, you can increase, you can multiply this by some number, let's say -10 into this, -10 into this. So this will just increase the length of this decision boundary, and 10 into this one. I'm just increasing so that it spans across the dimensions of the y-axis. So 10 into this. So this is a decision boundary. On the right hand side, whatever data point comes will be in positive class. On the left hand side, whatever comes will be the negative class. So this is the result that we are getting from perceptron. This is our weight vector, and this is our W transpose X.
We can apply this weight vector then to our test data.
Yes, correct. So on this very data, if we apply this weight vector, what will be the loss? Can anybody tell me?
0.
Correct. So we can cross check that quickly. We'll just use the final weight vector. No update, nothing. We'll just use the final weight vector. We'll apply it to each data point. Let's start this loop for I in range. Length of X. Let's compute Y pred as per this W. Y pred will be 1 if W transpose X I greater than equal to 0, else it will be -1. So this is our Y pred. Now we'll compare Y pred with the actual value of Y, which is Yi. So if Y pred is equal to Y I, which means they are matching. If they're not equal, which means there's a mistake, then we'll add, this is 0, 1 loss, right? So loss plus equal to 1. We'll add 1 loss. After this is done, let's print the loss. We're getting a 0 loss because as we have seen.
So here we are doing it after we've actually converged. Had we done this at each epoch, we would have gotten different losses, right?
Yes, correct. Yes. Okay, so this was a perceptron implementation on data which is linearly separable. Now we've written the code, actually, the entire code we have written. The other thing that you can try out is this thing. Let's say our data is not linearly separable, and there are some data points which are on the wrong side. So there is no linear decision boundary that can perfectly classify the two data points, the data points belong to two classes. In that case, how does perceptron behave is something that you might want to explore. You have written the code already. All this code you can make use of and apply it to a non-linearly separable data. So this code, if you use, this will be there in that collab. Here I'm using flip Y. This is used for noise. Earlier I had taken flip Y to be 0. I didn't want any noise. I didn't want any data point from here to go to the other side. Here I'm introducing some noise by having flip Y to be some value, non-zero value. The resultant data will be not linearly separable. I want you to apply this code again on that data and then see in each iteration what happens. You can keep track of, like somebody pointed out just now, we can keep track of loss in each iteration. We can see how many mistakes are happening in each iteration. Whether the perceptron algorithm is converging or not, you will see that it will not converge. So all this you can explore, experiment, play around. Okay. I leave this as an exercise for you. Any doubt in this code?
So basically in the question, if we don't specify the number of epochs, that like there'll always be a mistake, and like the for loop, it will not end.
Yeah, correct. So why we gave this 10 here? See, given any data, given any real world data, we wouldn't know whether it is linearly separable or not. And also real world data sets are not perfectly linearly separable. There is always some noise. So we want to give some upper limit. Otherwise, it will go on and on. Okay, like I said, in non-linearly separable data, it will go on and on. We don't want that to happen. We want some upper limit. For that, we give this parameter value.
Okay, I guess in this case, the most optimal solution will be the least loss. Yeah.
Right.
Ma'am, I was under the impression that perceptron can only be used for linearly separable data.
Yes, it can
once
only
once we've introduced noise, it will no longer be linearly separable. So how will we converge? Even
right,
if
it will
we
not
limit...
converge. That's what you will see. It will not converge.
So we just make best of whatever W we are getting in the epochs that we're
Yes, Yes, correct. You will stop at some point, and that at that point, whatever W is, you can make use of that.
But it won't really be optimal, would it?
You will never get an optimal optimal decision boundary if the data is not linearly separable. Okay.
Right.
Ma'am, epoch is the number of iteration or number of mistakes?
Iterations. Epoch is synonym to iterations. Okay.
Yes, ma'am.
Just one more question. Now we have specified epochs to be 10, and we are finding the loss at the end of each epoch, right? I mean, here epoch is just a hyperparameter. How do we decide what loss is acceptable?
Yeah, so this is called hyperparameter tuning. This epoch which is maximum number of iterations that should be tried, is a parameter in this technique, perceptron technique. Every technique has some hyperparameters. So given any data, how do we decide hyperparameters? We try out different values. Okay, that's how we practically proceed. We try out different values of these hyperparameters, and we choose the best value as per minimum loss or maximum objective function value, whatever that is. Okay.
The hyperparameter thing is totally human dependent process, or like we have some algorithm to follow.
But there are libraries which automate this process. In sklearn, there are libraries which automate this process. We can do it manually also. But yes, there is no magic wand that will give you this is best for your data. There has to be code, and these libraries do that only. Right. So they don't, they don't perform any magic. They try out different values of hyperparameters and their combinations, and they tell which one works the best on an average.
Is it necessary, like after each epoch, the loss will go down? Or it
if
can,
the data is linearly separable, if it is not linearly separable, it will not go down. It might fluctuate. It will keep going up and down.
So like
So in that case, we have to go back to the previous epoch.
So like we can
no, you can stop at some point.
Like so, like the most optimal boundary would be like something which we choose.
Yes. So there might be slight. For example, you might move from loss of 11, 10, 11, 10, 12, 11, 10. It might be like this. In fact, I guess if you run the code on this data, you might get something like this. I want to leave it for you to experiment. So something like this you will get. So let's say you stop at this point. This is your loss. If you stop at this point, this is your loss. So this will be close, right? But it will never converge. That is for sure. Your line might keep moving from here to here, probably like this, right?
Yeah.
It will never converge. That's how perceptron works.
So in this case, like we can choose either of the weight vectors corresponding to the 10-10 process.
Yes. If you want to be particular, you make a note of the loss, and then if it is increasing, you stop. Getting me? If it is increasing, you can stop like that.
But there's a possibility like it can go like to 9 also after.
It
maybe.
may or may not, but you will see the pattern in few iterations. You will be able to see the pattern that it is kind of repeating. That is what happens with perceptron. It goes back and forth. Okay. So you'll be able to see the pattern in few iterations, and then accordingly you can make a decision. You can keep a track of these losses. So you can take the minimum one and probably take this weight. Okay.
Okay.
So in sklearn also, the perceptron implementation, it tries out different values and take the least one. Because if the data is not linearly separable, you have to stop somewhere. Okay. And you have to use some weight value. So the one which is giving you the least loss is finally reported by the algorithm.
Ma'am, are we going to only cover perceptron today, or will we be moving on?
I'm sorry, Divya?
Are we concluding now at perceptron, or are we continuing today's session?
Yeah, we are going to conclude now. We are going to close soon now. The next topic will be covered tomorrow.
Would that be SVN?
Yes.
Ma'am, one quick question. Yeah, as tomorrow is going to be the last day for this workshop.
Sorry, what?
Tomorrow is going to be the last day for this workshop, right?
Tomorrow will be the last day, yes.
Yeah. So we are not covering pandas at all. Any reason for that? Are we not going to use pandas in MLP course?
So in MLT, we use Numpy library to implement things from scratch. Pandas is used more for data manipulation when we have real world data, huge amounts of data. So MLP will have pandas component.
Okay, in MLP we'll learn panda, huh?
Yes.
Okay, and just towards the end you said that while implementing Perceptron using sklearn, so does it mean that we can implement the same algorithm using two different libraries, right?
Sorry, I couldn't get you. Please repeat.
Just now, a couple of minutes back, you said that while implementing Perceptron using sklearn library, right? So does it mean that the one algorithm can be deployed using two different libraries like Numpy or sklearn?
One algorithm can be deployed. You mean implemented?
Yeah, can be implemented. Yes, not deployed. Implemented using two different libraries, right? Numpy also and.
See, Numpy you're doing from scratch. sklearn has it already. You will just use the already coded.
Okay, inbuilt function and all.
Yeah.
Okay, thank you.
So in a way, we can say that if you really want to do it practically, sklearn is the best. But if you want to understand the whole process, then Numpy would be a better.
Yes, definitely. Yes, that's what it is.
Thank you, ma'am. Nice.
Okay. I hope it was useful. I hope
extremely so. Very, very nice session.
Okay, good. That's good to know.
Ma'am, please upload the recording.
Recording will be there in you.
There is an Excel sheet actually shared over the same folder.
Yeah, so you will get it. Yeah, recording the studio team will take care of. You'll soon get the recordings. Yeah.
Because in the Google Colab sheet, there is no answer, only question.
Okay, do you want me to do it tonight or tomorrow? Can I do it? Tomorrow morning,
tomorrow,
can I? Okay.
Tomorrow.
Sure. So tomorrow morning, I'll copy the codes, the solution codes.
Okay, ma'am. Also upload video link, ma'am. It will very helpful.
Yeah, definitely. You will get the recordings. Definitely.
Thank you, ma'am. Thank you.
Thank you. It's an interesting session, ma'am.
Okay, thanks everyone.
Ma'am, just
thank you, ma'am. Thank you for the very detailed session.
Yeah, it's good to know.
Actually, I'm from a non-programming background. I did Python some 2 terms ago. So although I understood everything that you were doing, I'm not very confident about being able to code all that you have done.
Practice. That's all I'll say. That's all I say. Keep practicing. Until you get it, keep practicing. You'll get it. And you'll feel very high. Coding is like that. Seriously, coding is like that. Yeah.
Are there any say examples of books from which I can refer so that I can compare my answers?
So many books, so many resources, so many online articles. There's no dearth these days for content. You search for something, you get so many things. You just have to start somewhere.
All right.
Yeah.
Thank you.
Okay. All right. I guess we can close it now. It was a nice interaction with you people. So I hope you will practice and explore. If we went a little fast, we had to because we had to cover 2 topics. I understand we had to go a little fast in the beginning, but I hope we still did justice to these concepts and you understood them. So please practice and explore, and I'll copy the code tomorrow. Thanks everyone. Take care. Good night.
Thank you, ma'am.
Thank you, ma'am.